Good morning, students. So we'll move on to the next topic, that is assembler algorithm and data structure. Okay. Before I move on to the original concepts of assembler algorithm and data structure, first I would like to mention what type of algorithm we are using for the assembler. Fine. See, usually user used to write the assembly level language. Is it right? So that should be converted into machine level language. Is it? The machine level language means what? The object program, what we are calling it as, right? A hexadecimal series for the operation code and for the operand we need to generate. Yeah. For this, what we need to do is we need to scan our program complete. Fine. We need to have a categorization for which are should be considered as a operand and which should be considered as the operation code. Fine. And here we are also using some labels. Okay, we are also using some assembler directives over here. Is it? Okay. So our algorithm must be in a case of two phases exactly. We are calling it as first pass or pass one. Okay. And second, we are calling it as pass two exactly. Okay. So what is the technicalities residing in the pass one? We'll see first. Okay. Then we will be going for pass two exactly. Okay. Then what is this data structure? Why we need this data structure concept in assembler? Okay. See how we are having linked list, queues, stacks, arrays, and all. Okay. In case of C programming. Okay. Here we are using some tables for managing and holding the information. Yeah. See, in case of C programming data structure, we are using those type of linked lists and all. Okay, whatever I had mentioned. Okay, so we are using that for what? Holding them in such a fashion that retrieving should be simple. Is it right? Okay. Then manipulation of information should be simple. Yeah. For that, we are using what? A data structure. Fine. Okay. See, example of a library. If I take here in your college, there will be a different section for different branches. Is it right? Right. If I mix all the books together, okay, randomly, if I start placing books, okay, then student will be busy with finding the books itself. Okay, then later they need to find the concept. Is it right? So such type of problem we should not arise. Okay, in case of assembler. So what we are doing, we are using some data structure over here. Okay, using which we can organize our information in a proper fashion. Okay, then whenever the assembler is expecting the information, we can easily retrieve it. Yeah. Okay. So first I will be discussing about the data structure. Later we'll go for the algorithm. Okay, because first we need to understand what type of data structure we are using, then we'll go for algorithm. Okay, so our assembler uses two major internal data structures. Okay, there are two major data structures we are using over here. One is operation code table. Okay, in short form we are calling it as OPTAB. Okay, or OPTAB we are calling it as operation code table. First one. Second one, symbol table. Okay, SymTab we are calling it as. So in my further presentation, if I use OpTab, then it will be called as operation code table. SymTab for symbol table exactly. They are just two different tables. That's it. Okay, operation code table, which is defined by the assembler itself. It is inbuilt. Okay, the symbol table, it depends on the program what we are writing. Got some idea? Okay, operation code table, they are the inbuilt operation codes, okay, or else operation statement, whatever we are using in our program. Regarding that, we'll be having some information. Okay, they are inbuilt. Okay, static. They are static. We are calling it. Okay, but symbol table are dynamic. Okay, it all depends on the programmer what all the symbols they are going to use in his program. According to that, we will be designing the symbol table. Okay, now we'll see what is operation code table or OPTAB. Is used to look up mnemonic operation codes and translate them to their machine language equivalents. Okay, is observed is used to what? Look up mnemonic operation code and translate them to their machine language equivalents. Okay, so here in operation code table, just consider we'll be having two different columns. In one column, we'll be using to mention the mnemonics, what all we are using in the assembly level languages, example like add, store, then subtract, load, okay, statements for the accumulator and all. Okay, so those all mnemonics, inbuilt mnemonics, what all we are using, right? So that will be mentioned in one particular column. In the next column, appropriate opcode will be specified. Okay, opcode is nothing but your machine language equivalent. Okay, in my previous example, for storing the accumulator or for storing the link register, we were using a hexadecimal number called as a 1414. Okay, from where we are retrieving that from this operation code table itself. Yeah, whenever we encounter any kind of such type of a mnemonic, okay, assembly language mnemonic, first your assembler will refer the operation code table. So it will just find that particular mnemonic in the table. In front of that, what hexadecimal number is stored, that will be generated as an object code. Remember this. Okay, so this is why we are using operation code table. Now we'll go for the symbol table. We'll go in deep in the next further slides. Okay, but for your information, I'm just saying it. Okay, symbol table is used to store values or else addresses assigned to the labels. Okay, see, labels, what all we are using in our program. Okay, sometimes we'll be using such type of labels like loop, okay, or else return address. So such type of labels, if you are using for any particular memory location, that those type of labels will be managed under symbol table exactly. Okay, if you find any one particular label, okay, that should be uploaded in the symbol table. Appropriate address of that particular symbol of that particular label should be also uploaded with respect to the symbol exactly. Fine. Okay. So that's why we are calling it as what? Symbol table. So it is holding what? The address of the label. That's it. Operation code table is holding the mnemonic with respect to that. What is the operation code or else a machine language equivalent? Okay, that should be maintained. In case of symbol table, labels with respect to that, what is the address of that particular label should be managed with that. Yeah. Then apart from this, we are also dependent on one counter. We are calling it as what? Location counter. Okay. The shortcut for location counter will be LOCCTR. Okay. LOCCTR, location counter. Okay. This is a variable used to help in assignment of addresses. Okay. So this will help us to identify, I repeat, this will help us to identify the addresses of the labels. Remember this, addresses of labels exactly. Location counter must be loaded with initial address of program. See, first, whatever may be the content of location counter, it should be overwritten when we begin with the execution of a new program. It should be overwritten with what? The beginning address of the program should be loaded to the location counter. Then, when we execute each line of code, okay, like example, one line of code you are having, just observe, okay, length of code should be added to the location. See, you are loading it with first what? The starting address. Okay, feel that 1000 is the starting address. Then in the first line of the program, okay, feel that total 6 different bytes of instruction we are having. Okay, so that will be executed. Then the 7th byte will be holding what? The next instruction. Is it right? Okay, so the 6th byte was the length of a particular instruction. So that should be added to the location counter exactly. Then 1000 plus 6, 1006 exactly. Next will be 1007. Is it right? So such type logic we are using to find the location of the particular instruction exactly. Fine. The previously 1000 it is the beginning address of the instruction, right? Total how many bytes we had in that 1000 location? 6 bytes we had. 1000 plus 6, 1006. Okay. So next will be 1007. Such type. So so when we reach labels or okay. So when we reach the labels, location counter will be holding its address. Okay. So this location counter we are using to identify what is the location address of a label exactly. Okay. For that purpose, we are using this location counter. Yeah. Okay. Not for any other reason. Continuously, we'll be going for like adding the instruction length for our location counter. So beginning address will be loaded first. Then instruction length will be loaded will be added to the content of location counter. It will be continuous. So whenever we are reaching, observe it very careful, whenever we are reaching such type of labels, okay, so location counter will be pointing for that location itself. Is it right? Okay, label location. So we will be grabbing the address from location counter. That's it. Okay, by this we can update the symbol table entry. Okay, so this will help us to update the symbol table entry exactly. Okay, fine. Next. Operation code table. Okay, so we'll go in deep regarding the operation code table. Okay, must contain mnemonic operation code and its machine language equivalent. Okay, in complex assembler, this table also contains instruction format and length. Okay, so usually, basically, the operation code table consists of two columns itself. First column, the mnemonic will be available. Second column, machine language equivalent code will be available. Okay, but in complex kind of assembler, okay, two more columns would be available. In the third column, what format? Okay, see in class number 2, I guess, we were discussing about the format of the instruction, right? Format 1, format 2, format 3, and format 4 example. What type of format of instruction it is, that can be identified. Okay, that can be specified in your operation code table, column number 3. Then column number 4, what is the total length of that particular instruction? Okay, that also can be identified exactly. See, why we are using this length? Because format 1 is having only 8 bytes, sorry, 8 bits. Format 2 will be having only 8 plus 2, 4 plus 4, 16 bits. Okay, and the format 3 is having 20 and format 4 is having 24. Okay, so such type of like bit variation we are having. So after specifying the format, okay, your length also must be specified exactly, right? Okay, so this is what the gesture of the object code is. Okay, so we'll see during pass 1 and pass 2 what is going to happen. Okay, during pass 1, OP tab is used to validate the operation code in the source program. Remember, if you are writing, if you are trying to write store L, what is the syntax? STL, that's it. If you are writing STRL, then that is a mismatch exactly, right? That is an error exactly. So such type of operation code, if you are specifying, or mnemonics, whatever we are specifying in our program, if there is an error, okay, that can be identified using the pass one. How it is? See, what mnemonic you are specifying in your program, okay, that will be compared with the operation code table exactly. If same thing is available in the operation code table, because it is a predefined, it is a inbuilt exactly. Same if it is available, then you don't create any kind of error. Otherwise, it will generate an error that mismatch or else the syntax error. Such type of error can be generated over here. Okay, so that is the benefit of using pass one algorithm over here. Then and pass two, they are replaced with machine language algorithm. During pass one, we are just scanning them whether it is a valid kind of mnemonic or not. In pass two, with respect to that second column entry, what we are having, that will be uploaded in the object code exactly. That's it. Okay, so this is what we are having, the logic which is residing under operation code table. Then OP tab is usually organized as a hash table. Okay, means like we need to search for a particular mnemonic, right? It is not like from first row to last row you are trying to search for a particular mnemonic. It will be taking a lot of time exactly. So we should use the mnemonic operation code as a key over here. Okay, whatever the mnemonic we are using, example store, right? Or store link register, STL. Okay, so such that should be the key for searching the table exactly. Okay, so we are using hash table, means particular value should be targeted over it. Okay, that's what we are calling it as a hash table. Then entries of table are predefined, and in most of the cases it will be static. Okay, so it is not like the user is uploading the value for the operation code or else value for the mnemonics and all. It is predefined, and it is in most of the cases it will be static. Okay, we are not altering them. Okay, it is from inbuilt itself. Then table search time will be simple due to usage of mnemonic as a key. Okay, so search time will be bit less. Okay, then we'll go for the symbol table. Symbol table includes the name and value. Value means address exactly for each label in the source program together with flag to indicate error conditions. Okay, so here as per the first point, we can identify there are total 3 different columns. One is for the label, second is for its with respect to address, and third is for the flags. Okay, for identifying the errors exactly. Now you may ask like what kind of error we may get in case of a label. See, example, we are having a label called as alpha. See that? Okay, we are having a label called as alpha, which is defined in an address called as 1000. Okay, feel that we have a location called as a 1000. For that, we are labeling it as a alpha. Okay, then later in 1056, we have one more location. There again, you are labeling it as what? Alpha. Okay, means 1000 and 1056 both are having a address label called as a alpha. Okay, so we are calling it as what? Duplicate error. We are calling it as duplicate error. We are not considering the 1056, we will consider the 1000 itself because Already we found alpha means what? 1000. We already updated in our symbol table. Second time, if you are finding the alpha itself with different address, that will be considered as a duplicate. Okay, that's why we are having an example called as, you just observe, symbol defined in two places. Symbol defined in two places. Okay, so such type definition, if it is available, then we are generating the error called as duplicate error. That will be neglected exactly. Okay, then this table may also contain other information about the data area or instruction label. Very careful. Data area. What is this data area exactly? See, sometimes we'll be using something called as a byte, reserved byte, such type. Is it right? Okay. Sometimes we'll be generating or we'll be using some label for it, holding the data. Okay. Such type will be available. One thing. Later, second will be instruction label. Sometimes, okay, for executing the loop condition. Okay, executing the loop condition. We'll be checking some conditions, right? If it is less than or if it is greater than, go to some particular location, jump to particular location. Then which is that location? There also we need to label. Okay, that is the label for the instruction exactly. Yeah, such type is also available. That also should be such type of information also should be available in our symbol table. Okay, fine. We'll see during pass one and pass two how the symbol table will be altered. We'll see that. During pass one, labels are entered into the symbol table as they are encountered in the source program. See, you'll be scanning the program during the first pass. Okay, first line to last line. Whenever you are finding such type of labels, you'll be uploading it for the symbol table here, along with their assigned addresses. Okay, from where? From location counter exactly. So symbol table will be updated based on the pass one. So if you are finding the particular label in front of the whatever the address is available, that will be known by your location contact. So that will be uploaded in the symbol table. During pass one, we are just grabbing the information, remember. But during pass two, symbols used as operands are looked up in symbol table to obtain the addresses to be inserted in the assembled instructions. Okay, so now during pass two, wherever you are using these type of labels or these type of symbol as a operand, everywhere that particular address should be uploaded. During pass one, what you are grabbing the information that will be utilized in the pass two. That's it. Okay, symbol table is usually organized as a hash table for efficiency of insertion and retrieval. Okay, so deletion will be very rare. Okay, regarding deletion, we don't have any information. Okay, like most of the cases, we'll be inserting and retrieving. That's it. Okay, so for one program, okay, once the symbol table will be updated, finally after the execution, when we terminate, then everything will be released exactly. So when we are uploading the next new program, like once again, the symbol table will be uploaded, will be updated. Okay, then the new entries will be given. So deletion of content will be very rare exactly. Okay, so now we'll see what is the job of pass one and pass two, and we will be discussing a pass one and pass two algorithm. Very simple. Okay, it looks difficult, but it's very simple. Okay, so assign addresses to all the statements. So this is what the pass one job, like the if it is a opcode, if it is a operand, whatever it is. So we need to assign the address first. Okay, save the address assigned to all the labels to be used in pass two. Okay, so it is regarding the symbol table. First one is regarding the opcode, second one is regarding the symbol table. Then perform some processes, perform some processing of assembler directives such as reserve word, reserve byte. Okay, to find the length of data area for assigning the address values. Okay, so this is also very important. Like reserve word, right? Reserve word. In front of that, how many it will be available? Then what we need to do? We need to multiply 3 with number which is specified in front of reserve word. See, example, if I want to reserve 2 different words, per word 3 bytes are available. So 3 into 2 exactly. So total how many words or how many bytes we are going to reserve over? Okay, total 6 exactly, right? Such time. Then in case of reserve byte also, okay, in case of reserve byte, here we are not multiplying, just we are reserving the number of bytes, that's it. Okay, such type of mnemonics or such type of directives if it is available, that also should be processed by your password exactly. Then later, defines the symbol in the symbol table. Okay, generate the symbol table, that's it. By utilizing all these information, we need to update our symbol table exactly. And here we got the symbol or else the pass one assembler exactly. Okay, pass one algorithm. See, very simple. let me take one example. See example, if you are having, okay, so this is the column for the label, this is the column for the instruction, okay, and this is the column for the operand. Feel that label, instruction, operand. Okay, sometimes here, okay, we'll be having some label, right, like loop. Okay, feel that it is a loop. Okay, so here we are having something called as store L, right, and here length. Okay, so length is a operand, store L is a instruction, and for this we are having a one label called as a loop. Okay, so this condition we are checking. See, for every instruction we need to check this time. See, this label may not be compulsory for each and every instruction, but for few it may be available. Okay, but this instruction is very, very important. Observe it very carefully. This instruction will be available for each and every line of the program. Okay, but remember one thing, but the operand, as I mentioned, the length, it may be available, it may not be available. Sometimes few instructions are available, like return subroutine, R sub. Okay, in front of that, we won't be having any kind of operand over there. Okay, we won't be available with the label for such type of instruction. Okay, so this condition just remember, okay, because I'll be taking such type of an example in this algorithm exactly. Okay, so pass one algorithm we have. The first statement will be begin. Okay, so just observe, read first input line. I have a program. I have a program. What is the first instruction? Or what is the first step of this pass one assembler is? Okay, see, we are trying to compile or we are trying to assemble it. Remember, okay. So now, what is the first step of this pass one? Read the first input line. Obviously, you need to read. Okay, now just observe. Just observe. If opcode is equal to start, if opcode is equal to start, actually this is a directory. Remember this. This is a directory. If the first line, if you are available with a start, okay, then what you need to do, okay, if opcode is equal to start, then begin. Just observe the second line. Let me take the okay, then next, what I need to begin with, save, observe it very carefully, save hash operand. Okay, see, this indicates, so whatever, okay, whatever the address of this start we are having, okay, that we are targeting it for, that we are targeting it for. Okay, so hash operand as start addresses. Okay, hash operand to start addresses means in our previous example of copying a file from input file to output or input device to output, okay, there what we had is start we had, okay, so in front of the 1000 we had, okay, so here 1000 is the operand exactly, start is the opcode, okay, or else start is an instruction and 1000 is the opcode exactly, so 1000 is the operand exactly. Okay, so hash operand means same 1000 it is, same 1000. Okay, it should not be considered as an address, it should be considered as a value exactly. Okay, so that should be considered as a starting address. Then initialize location counter to starting address. Okay, initialize location counter to starting address. As I mentioned, okay, during the data structure discussion of assembler, okay, we'll be having three things. One is the OP tab, one is the symbol table, and location counter. What should be the content of the location counter? Starting address of the program should be loaded to the location counter. That should be the first thing. Okay, so same thing we are doing over here. Then write lines to intermediate file. See, this intermediate file is an input for your pass-to exactly. Input for your pass-to exactly. Remember this. Okay, so whatever we are writing into intermediate file, that will be the input for the pass-to. Finally, we are generating the machine language instruction. Remember this. So this is the partial output we can call it as. Then after that, after this process, what we need to do? Read next input line. Okay, whatever the next input line we are having, okay, that should be read. Okay, then so we are terminating this if condition. Okay, if start. Okay, condition if start. Okay, then we'll be going for. Okay, we'll be going for else initialize location to 0. Initialize location to 0 means if the opcode first line of the program, if it is not equal to start, then initialize location counter to 0, means nothing is there to execute, nothing is there to scan exactly. Okay, see, for the beginning of the program, it should begin with a directive called as a start itself. It should end with a directive called as end itself. Okay, if there is no start in the first line, it indicates that we don't have a program itself. Okay, that's why, okay, if it is not the case, if it is not equal to start, then end of the start it will be, then else condition we are having, initialize location counter to 0 exactly, which we don't have any program. Okay, later, okay, if that is not the case, okay, while opcode is not equal to end. Okay, see, after doing this, we are reading the next line, right? We are reading the next line, right? Now, after while reading that next line, the opcode, whatever you are having, if that is not equal to end, means we are trying to find whether we are encountering end of the program or not. Okay, if you are not finding the end of the program, then we need to perform this procedure. Okay, we need to perform this procedure. Just observe my cursor. Okay, we need to perform this procedure exactly. Then, if it is not equal to end, then begin. If this is not a comment line, okay, so the next line of the start program, okay, if it is not a comment line, okay, then what we need to do? We need to begin again. If there is a symbol in the label field, see, as I mentioned, first will be label, second will be instruction, and third will be the operand. Okay, so second line we are reading now. If there is a label in this particular instruction, okay, then begin. Search for the symbol tab for label. Okay, we need to search for the symbol table whether this label is already existing or not. Okay, fine. If it is already existing, what will be happening? If it is not available, then what will be happening? We'll see that. Okay, search symbol table for label. If found, then if it is already available, then set error flag, because see, the address of this particular location is a value of this particular label exactly, right? Means I told you, right, duplicate error. Okay, like twice if you are defining the address of the label, then it should be generating duplicate error exactly. So set error flag duplicate symbol. Else, otherwise, if it is not available, insert symbol, insert that particular label, okay, label name with location counter, okay, into symbol table. Okay, fine. So that is what we are updated with the label. Next, what we need to do? We need to go for the instruction, right? Okay, fine. Such for okay, fine. It's okay. End. Okay, if symbol, wait a second, symbol table. Okay, if symbol, end of the like if statement. Okay, found then symbol table regarding the symbol already end. Okay, search op tab for opcode. Okay, so here whatever we are having, right? Okay, for that regarding we need to search for the op tab exactly. If found then, so whatever is mentioned in this particular location, if it is found, add 3. Okay, instruction length, usually 3 bytes we'll be using. Okay, 3 bytes to where? I think I missed. Such operation tape for opcode. Okay, if found, then add 3. Okay, instruction length to location counter. Okay, that should be done. Okay, else, okay, if opcode is equal to word, see, sometimes we may get, okay, after label, sometimes we may get word, okay, then reserve word, reserve byte, such type. If it is opcode, then go for the operation code table, okay, then update the location counter with 3 exactly. Then if it is a word, if such something we are writing it as a directly called as a word, okay, then what we need to do? Add 3 to location counter. Add 3 to location counter exactly. Word means what? Like one word operand it will be. One word operand it will be. That's why we are adding the 3 for the location counter. Else if opcode is equal to reserve word, observe it very carefully. Reserve word. We need to reserve the word. Now the question arises, how many? Now the question arises, how many? Okay. In front of this reserve word, in the operand location, will be specified with how many number of words we need to reserve. Right? Okay. So that we are trying to add over here. Add hash operand to length exactly. Oh, sorry, not this one, the previous one. Add 3 into hash operand. See, 3, why we are writing one word is 3 byte exactly. Now, in front of that, some operand is specified that indicates what? That indicates how many number of words we want to reserve. That's why that how many number will be specified by hash operand into 3. Whatever the length we are going to get, that will be added to location count. Okay, else if opcode, if it is equal to reserve byte, then okay, how many number of byte you want to reserve? Okay, that we are considering as a hash operand, so that will be added to location counter. Else if opcode is equal to byte, if it is there, then okay, begin. So if it is a byte, then find length of constant in bytes, add length to the location counter. Okay, so end of the byte. Okay, if these are not the cases, if it is not a content of opcode, if it is not a reserve word or reserve byte or byte, okay, so end of the byte, then else set error flag invalid operation code. So this place is invalid exactly. Okay, so that is what we are checking. Then end of is not a comment, write line to the intermediate file, then read next input line. Okay, so end, while not end means we need to go for this condition again, then we need to check whether it is a comment line or not. Then if it is there, label, okay, such type of everything should be performed it again exactly. Okay, until we find equal to end. Okay, then write last line to intermediate file. Okay, save. Wait, I'm not able to read it because of my toolbar. So let me refer the textbook. What we have. Okay, so the last line is save location counter minus starting address. See that last line, what we are having is save within a bracket location counter minus starting address as program length. We need to identify what is the length of the program. That is very important. Okay, because that should be identified, that should be mentioned in the object code. Do you remember in the header file, H is the indication for the header file, starting address of the program, sorry, name of the program, then length of the program should be identified over there. Okay, by what means we are identifying? By because of this. Okay, so location counter is holding, like when we are reading each and every line, we will be adding the length of that particular instruction. So if you are subtracting the starting line with the starting address with the location counter value, then you will be finding how many number of bytes you are with this particular program. So that will be identified. Okay, so end pass one. The next last line will be end pass one exactly. So this is how we are scanning our complete program exactly. Okay. Okay. Now we'll go for pass two. It's very simple. Assemble the instruction means translate operation code and looking up addresses. Okay, generate data value defined by bytes, word, whatever. Okay, perform the processing of the assembler directly, not done during the pass one. Okay, write the object program and assembler listing exactly. Okay, same thing what we have done by program pass one. Okay, same thing should be done by your pass two also. Okay, it's very simple compared to the pass one. It is simple exactly. Begin. Read first input line from the instruction file or intermediate file. Okay, if opcode is equal to start, then begin. Write listing line. Okay, read next input line. Okay, see here what we are trying to do is here we are generating the header record exactly. Okay, so after this, what we are doing here, we are just generating the header record. Right, header record to object program. Okay, initialize first text record. Okay, so after this, after utilizing this information, we'll be writing the header record for our object program. Then we are initializing the text record. Okay, and now we are checking if the opcode is not equal to end, then same procedure. Okay, if this is not a comment line, then begin search for the operation table for opcode. Okay, if found, then begin. Okay, if there is a symbol table in operand, if there is a symbol in the operand field, then begin search symbol table for the operand. If found, then store symbol value as operand address. Means after the operation code or after the what we are calling after the mnemonic. Okay, if you are available with some kind of a operand, okay, where it is stored in regarding that information should be uploaded. Okay, so that is what we are doing over here. Else begin store 0 as operand address. If it is not found, then it will be stored as 0 as operand address. Set error flag undefined symbol exactly. Okay, end of this particular if statement. Okay, then end of this symbol. Then else store 0 as operand address. Okay, assemble the object code instruction. Okay, and if opcode found, okay, so this particular like opcode, if it is found, okay, so that will be terminated over here. Okay, and if opcode is equal to byte or word, then convert constant to object code. Okay, if object code will not fit into the current text record, then begin. You need to go for the new one. Okay, write the next text record to object program. Okay, initialize new text record. Okay, we need to go for a new one. Then same thing, we need to terminate each and every condition, whatever we are using over here. See, in past one, whatever we did, okay, like whatever the information we are grabbing, okay, that will be just uploaded in the object program. That's it. Okay. Pass two is not going to verify anything. So it will just refer the operation code table and it will just refer the symbol table. Whatever the respective information is available for that particular instruction, that will be uploaded. That's it. Okay. So here, when we are coming to the end, okay, end of the program, right? Last line text record to object program. Okay. Right. End record to object program. Okay. Right. Last listing line exactly. So if you are completing this procedure, pass through assembler, then header, text, and end. Okay, in the previous lecture, what we discussed, the format of the object code that will be generated exactly. So this is it for our students. Okay, so just please go through this particular algorithm because you need lots of time to understand this particular algorithm. Okay, invest some time. Okay, you will find what is the logic we are using. Okay, students, thank you.